Earth, our home for 4.5 billion years. A world that has seen ice ages come and go, continents drift, and life rise and fall through countless natural climate shifts. But what we're living through right now is different. This is the fastest warming in recorded history, and it is driven by us. This is the story of how humanity discovered climate change, what causes it, and most importantly, what we must do next. Climate change is real, it is human-caused, and it is accelerating. It's a journey of scientific discovery, overwhelming evidence, and a growing global response. The good news? Today, we have the knowledge and the tools to act. Join us as we uncover the full story and the path to a better future. Climate change is a long-term shift in global or regional climate patterns, particularly the rapid warming we've experienced since the mid-20th century. Throughout Earth's history, the climate has always varied naturally. Ice ages have come and gone, massive volcanic eruptions have cooled the planet temporarily, and subtle changes in the sun's energy output have influenced temperatures over long cycles. These natural forces caused gradual shifts that unfolded over thousands or millions of years. But what we're seeing today is fundamentally different. The current warming is happening at a speed and scale that is unprecedented in the entire record of human civilization, and even in paleoclimate records stretching back hundreds of thousands of years. Since pre-industrial times, global average temperature has already risen by approximately 1.1 degrees Celsius. That sharp upward spike in the famous hockey stick graph represents a dramatic departure from the slow, natural fluctuations of the past. The critical distinction we must understand is this: natural climate variability versus human-accelerated or anthropogenic change. The rapid warming we're witnessing now is overwhelmingly driven by human activities, and recognizing that difference is the foundation for everything that follows in this story. In the 19th century, scientists began to unravel one of nature's most essential mysteries: why Earth is warm enough to sustain life. They discovered the greenhouse effect, a natural process in which certain gases in the atmosphere act like a blanket, trapping heat from the sun and keeping our planet at a habitable temperature. The story begins in 1824, when French mathematician Joseph Fourier first proposed that the atmosphere traps heat, much like glass in a greenhouse. In 1859, Irish physicist John Tyndall took the next crucial step. Through careful experiments, he identified water vapor and carbon dioxide as the primary gases responsible for absorbing and retaining heat. Then, in 1896, Swedish scientist Svante Arrhenius made a groundbreaking calculation. If we were to double the amount of CO2 in the atmosphere, global temperatures would rise by approximately 5 to 6 degrees Celsius. What these pioneers described was a perfectly balanced natural process, one that has kept Earth livable for millions of years. But today, that same process is being dangerously enhanced by human activity. We are adding unprecedented amounts of greenhouse gases to the atmosphere, thickening the blanket and driving rapid, uncontrolled warming. Understanding the greenhouse effect and how we are now disrupting it is fundamental to grasping the full scope of the climate challenge we face. In 1938, a British engineer named Callendar made a startling discovery. By meticulously analyzing decades of temperature records and atmospheric measurements, he demonstrated for the first time a clear link between rising human carbon dioxide emissions and increasing global temperatures. Callendar showed that the CO2 we were releasing from burning coal, oil, and gas was already beginning to warm the planet. His calculations and graphs were remarkably accurate, even by today's standards. Yet this early warning went largely unheard. The world in the late 1930s and 1940s was consumed by far more immediate crises: the Great Depression, the rise of fascism, and then the devastation of World War II. Survival and recovery took absolute priority. In the aftermath of the war, as nations rebuilt, fossil fuel use exploded. The mid-20th century saw an unprecedented surge in coal-fired power plants, automobiles, and industrial production, driving economic growth but also pouring vast new quantities of CO2 into the atmosphere. The science was there, the evidence was mounting, but global attention was elsewhere. Callendar's insight, though published and discussed in scientific circles, was effectively sidelined for decades. The world simply wasn't ready to listen. That missed opportunity set the stage for the much larger challenge we face today.
In 1958, a young scientist named Charles David Keeling carried a new kind of CO2 analyzer up to the remote Mauna Loa Observatory in Hawaii, determined to measure the breadth of Earth's atmosphere with unprecedented precision. Week after week, his instrument traced out a jagged line. CO2 dipped as plants grew in spring and summer, then rose again in autumn and winter. But beneath that natural rhythm, the whole line was climbing higher each year. This simple graph became known as the Keeling Curve, and it provided the first clear, continuous evidence that carbon dioxide was steadily building up in the air because of human activities, especially the burning of fossil fuels. When Keeling's record began, CO2 was only about 315 parts per million. Today, readings at Mauna Loa regularly exceed 420 ppm and are edging toward 430 ppm, levels not seen for millions of years. The Keeling Curve is more than a line on a graph. It is a visual warning that each year we delay action, we push the planet's atmosphere further into uncharted territory.
By the 1980s, the science had become too strong to ignore, and the world started building institutions to turn climate knowledge into climate policy. In 1988, the Intergovernmental Panel on Climate Change, the IPCC, was created by the World Meteorological Organization and the UN Environment Program to bring thousands of scientists together to assess what we know about climate change, its risks, and possible responses. For the first time, governments asked the single global scientific body, "Tell us, as clearly as you can, what is happening to the climate and what we should do about it." Just a few years later, in 1992, countries met in Rio de Janeiro and signed the United Nations Framework Convention on Climate Change, or UNFCCC, the first global treaty whose goal was to prevent dangerous anthropogenic interference with the climate system. It created a standing process for annual climate talks, where IPCC reports would feed directly into negotiations about emissions cuts, finance, and adaptation. Across the IPCC's assessments, the language on human responsibility grew steadily stronger, from cautious phrases about a discernible human influence in the 1990s to extremely likely that humans were the main cause of recent warming, and finally to today's conclusion that human influence on the climate system is unequivocal. In other words, what began as a scientific question had by the late 20th century become a matter of global policy, and the world could no longer claim it didn't know.
When we talk about the enhanced greenhouse effect, a few key gases dominate the warming, and they mostly come from activities we control. Carbon dioxide is the heavyweight, responsible for roughly 3/4 of global greenhouse gas emissions once everything is converted to CO2 equivalent. Most of it comes from burning coal, oil, and gas for energy and transport, with an extra push from deforestation and land use change that both release carbon and remove forests that would otherwise absorb CO2. Methane is a smaller slice by volume, but far more powerful at trapping heat in the short term, and it accounts for around 1/6 of global emissions.
Human-driven methane comes mainly from agriculture, especially livestock and rice, leaks and venting from fossil fuel production, and the breakdown of organic waste in landfills and wastewater. Nitrous oxide and fluorinated gases together make up the remaining share, but pack an outsized punch per molecule. Nitrous oxide is largely released from agricultural soils and nitrogen fertilizers, while fluorinated gases, used in refrigeration, air conditioning, and some industrial processes, can be thousands of times more potent than CO2 over a century. Taken together, these gases have pushed their concentrations well above natural background levels, strengthening the greenhouse blanket around Earth and trapping far more heat than the planet would under pre-industrial conditions. Understanding which gases matter most and where they come from is essential if we want to cut emissions fast enough to stabilize the climate.
Our modern fossil-fueled economy is the main cause of today's rapid climate change, and its impacts are already unfolding around us. In just a few decades, we have built an energy system, transport networks, industries, and food production methods that depend heavily on coal, oil, and gas, as well as on intensive farming and large-scale land use change. Power plants, cars and trucks, factories, cattle herds, rice paddies, and deforestation together form the core human-driven greenhouse gas emissions, pushing atmospheric CO2 and other gases far beyond natural levels. The consequences are already visible. Seas are rising as ice sheets and glaciers melt and warmer water expands, threatening coasts and low-lying islands. Heat waves, heavy rainfall, droughts, and wildfires are becoming more frequent and intense in many regions, while ecosystems struggle to cope, driving biodiversity loss on land and in the oceans. These changes strike at the foundations of human well-being by undermining food and water security. Shifting rainfall patterns, more frequent droughts and floods, and rising temperatures reduce crop yields, stress water supplies, and increase the risk of hunger and displacement, especially where people depend directly on rain-fed agriculture. And although climate change is a global problem, it does not affect everyone equally. Vulnerable regions and communities are hit hardest despite having contributed least to the crisis. Low-income countries, small island states, and marginalized groups face a dangerous combination of high exposure to climate hazards, reliance on climate-sensitive livelihoods, and limited resources to adapt, turning climate change into a powerful driver of inequality and injustice.
Tackling climate change is not just about technology. It's about transforming political priorities, economic systems, and questions of justice all at once. Politically, the world still struggles to act as one. National interests, lobbying by fossil fuel industries, and election cycles that reward short-term gains often block the long-term cooperation deep cuts in emissions require. Even when leaders sign ambitious agreements, shifting governments and competing priorities can slow or reverse progress, creating a dangerous gap between promises and real-world action. Economically, we're tightly bound to fossil fuels, and unwinding that dependence comes with real transition costs. Phasing out coal, oil, and gas risks stranded assets worth trillions of dollars and major disruption for workers and regions built around these industries, which makes governments and investors cautious, even when clean alternatives are ready. At the same time, climate change is an equity challenge. Developing countries need space and support to grow their economies without repeating the high-carbon path taken by today's rich nations. That means scaling up climate finance, technology transfer, and capacity building so that clean energy and resilient infrastructure are affordable options, not luxury choices. All of this is happening under intense time pressure. To keep warming within safer limits, global emissions must peak soon and then fall rapidly toward net zero. Every year of delay locks in more fossil infrastructure, narrows our options, and shifts a heavier burden onto younger and more vulnerable generations, making inertia and inequity the twin obstacles we must overcome. Solving climate change means cutting the pollution driving warming and preparing for the impacts we can no longer avoid, and we already know how to do both. Mitigation is about turning down the heat at its source by rapidly decarbonizing every sector of the economy, replacing coal, oil, and gas with renewables, making buildings, industry, and transport dramatically more efficient, electrifying as many end uses as possible, and using targeted carbon removal to deal with the hardest to abate emissions. Pathways consistent with limiting warming to around 1.5 degrees Celsius show deep cuts in fossil fuel use, a massive scale-up of wind and solar, widespread electrification, including electric vehicles and heat pumps, and some use of carbon dioxide removal, such as reforestation and engineered options. Adaptation focuses on living with a changing climate by reshaping our infrastructure, systems, and ecosystems so they can withstand more heat, floods, storms, and droughts. This includes climate-resilient infrastructure like flood-resistant roads and power systems, early warning systems for extreme weather, and restoring ecosystems such as wetlands, forests, and mangroves that buffer communities against storms and sea level rise. To keep the Paris Agreement's 1.5 degrees Celsius goal within reach, global CO2 emissions need to fall steeply and reach net zero around the middle of this century, with total greenhouse gas emissions reaching net zero a bit later. The later emissions peak and the slower they decline, the more we risk overshooting 1.5 degrees Celsius and relying on large-scale carbon removal later, which is costly and uncertain. The message of hope is that the core technologies for this transition already exist. Their costs have fallen dramatically, and real-world action is accelerating. Solar and wind are now among the cheapest sources of new electricity in many regions. Batteries and electric vehicles are scaling fast, and more countries, cities, and companies are committing to net zero targets. Proof that a cleaner, safer future is possible if we choose to move quickly enough.
If this video helped you see the bigger picture on climate change and what we can do about it, consider subscribing to the channel so you don't miss future episodes. You'll find more videos here on climate science, energy, and sustainability, from deep dives into the data to practical solutions you can apply in your own work and daily life. Before you go, take a moment to explore the playlist and check out the other climate and sustainability topics we've covered, and let me know in the comments what you'd like to see next. Together, we can turn knowledge into action and help drive the transition to a more sustainable, climate-safe future.